Welcome back. Today I want to go ahead and discuss Lesson 7.3, similar polygons and triangles. So similar polygons. Similar polygons have the same shape, but not the same size. Now, two polygons are similar if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. So let me go ahead and demonstrate. Suppose that I have a rectangle, and we know with a rectangle, each angle of a rectangle is 90 each. So this is my original figure. If I were to copy and then paste, notice we have the same figure, right? I'm comparing one figure to another figure. The angles are the same, the sides are the same, so these two figures are congruent. Now, if I were to enlarge in this figure, well, this figure came directly from this smaller figure. And we know that the angles are the same and these shapes are the same, but the sizes are different. So we say that these figures are similar, okay? So let's go ahead and look at this example here. In the diagram below, ABCD is similar to WXYZ. So in order for us to figure whether or not these two figures are similar, we have to look at their corresponding angles and we have to look at their corresponding sides. So I'm looking at angle A. Angle A is congruent to angle W because they have one arc. And then we can see that angle B is congruent to angle X. And then angle C has three arcs, so it's congruent to angle Y. And then angle D, four arcs. Angle Z, four arcs, so those two things are congruent. So we have corresponding angles. Now the corresponding sides, not the angles, we look at AB. Notice that AB, okay, so the A has one arc and the B has two arcs. I need to find that side with 1 and 2. So here's a side with the 1 and the 2. So we know that AB corresponds with WX. And then BC corresponds with XY. And then CD corresponds with YZ. And then DA corresponds with ZW. So then, what is our ratio here? Well, if I look at 18, that's part of AD, and we know that AD corresponds with WZ, so I can create a ratio from 18 to 6. So 18 to 6, this is our ratio, but what is the problem here? It's not simplified, so we're going to go ahead and simplify that to 3/1. So this is our simplified ratio, okay? To make things easier, if you know that these two figures are similar from the beginning, right? So we can just take a look at their similarity statement. So I have A, B, C, D is similar to W, X, Y, and Z. So if I look at A, the first position, it corresponds with W because their angles are congruent. They are corresponding angles. If I were to look at B, it corresponds with X, C corresponds with Y, and then D, since it's the last letter for this statement, it should correspond with the last letter of this statement. So D corresponds with Z, okay? And those, what I'm saying, they are in terms of corresponding angles. Now, if I were to talk about the corresponding sides, I have A, B, the first two letters, they correspond with WY, and then CD corresponds with YZ, and so on and so forth, okay? So, this 3/1 that we found here, is what we call our scale ratio, okay? That's me figuring out one side to another side, and hence I got the 3/1 here. We call that our scale ratio. Now the scale ratio is the ratio of corresponding side lengths of two similar polygons. So if I were to say, in the diagram, triangle ABC is similar to triangle XYZ, well, great, we can assume that these two figures are similar. Now, for me to create a scale ratio, I'm going to look at one number to another number. So here I have AB, okay? So it says the scale ratio triangle ABC. So find the scale ratio from triangle ABC to triangle XYZ. I know that AB is 6. It's the first two letters. They correspond with XY. So then I can create a ratio from AB to XY. So AB to XY is 6/3. But what's the problem? The problem here is that, yes, this is a ratio, but it's not simplified. So we need to simplify that to 2/1. Okay? So 6/3 is equal to 2/1. Go ahead and use a different color. Now I got to go ahead and find the scale ratio from triangle XYZ to triangle ABC. So I'm looking at the smaller figure to the bigger figure. So XY, it corresponds with AB. And it says right here, XY corresponds with AB. So the first two letters to the first two letters. So XY over AB is 3/6, which reduces to, 1/2. Okay? So that's how you find the scale ratio. Now, what I need to do here, for example 4, is just determine whether the triangles are similar. If so, write the similarity statement in scale ratio. Okay, so how I like to approach this is that I can see that all these sides here, they all have numbers. They don't have any variables whatsoever, so I need to do this. Since we have our bigger triangle here and our smaller triangle here, I'm going to look from, the smallest to the smallest side, the second biggest to the second biggest side, and then the largest to the largest side. So let's go ahead and take a look at this. This one is pretty easy. I have NQ, which is between this first arc and the two arcs here. One arc and the two arcs here. So that should be, if I were to look, okay, so this is the second biggest side. So if I were to look over here, 10 is the second biggest side of this triangle, and it's between this one arc and the two arcs here. So I can say NQ corresponds with RS, and NQ is 12.5, and then RS is 10. So I'm going to express these two numbers as a ratio. Now let me go ahead and simplify that, and I'm going to use my calculator for this one, okay? So then I'm going to write 12.5 divided by 10. I'm going to hit enter, and you should see 1.25. Now under the alpha button, you should see the word math. Click on that, and you should see all these options here. You're going to click on the first one or highlight the first one and press enter twice. And that should convert from a decimal to a fraction. And that decimal is going to turn into a simplified fraction. That's what you want. So you don't have to figure out what number goes into 12.5 and 10 at the same time. You can use it with your calculator. So 12.5 over 10, that simplifies to 5/4, okay? So this corresponded with this, and that's my second biggest side. Let's go ahead and find the smallest side. The smallest side of this bigger triangle is 11.5, so I need to find the smallest side of this triangle, which is 9.2. So then I'm going to write QP is to TS, and QP is 12.5, we already did that. It's 11.5 over 9.2, and that, I'm going to go ahead and go back to my calculator and do that again, what I did before. 11.5 divided by 9.2, hit enter, and I'm going to press math, enter. Okay, so I'm going to press enter, and then I get 5 over 4. I get 5 over 4. Okay? Alright, so now what I want to go ahead and do is I'm going to look at the last side, and that's the largest side. So 15 to 12, so it's NP is to TR. So it's 15 over 12, and I know that 3 goes into 15 and 12 at the same time, so it's 5 over 4. So look at that. We have these corresponding sides are proportional. So the corresponding sides are proportional. Now I need to figure out whether or not the corresponding angles are congruent. Note that you can see that angle N has one arc, and so does angle R for this other triangle. And then angle Q has 2, and angle S also has 2, so those two things are one corresponding to congruent. And then angle P and angle T, they are obviously congruent because of the third angles theorem. Meaning that if this and this are congruent and this are congruent, then this has to be congruent to that. So it has 3 arcs there. So then I got my scale ratio. So this is my scale ratio, 5 over 4. I got to go ahead and write a similarity statement now. So the similarity statement let's say we'll call this triangle NQP. So triangle NQP is similar to triangle, well, it corresponds with N, R, what corresponds with Q, S, and what corresponds with P, T. So that's how you write a similarity statement. Let's take a look at example 5. In the diagram, ACDF is similar to VWYZ. Find X and Y. So I have these two figures here, and we can assume that these figures are similar. So I can see from this bigger trapezoid, this shrunk into this smaller trapezoid. So it has a scale ratio. So the side lengths are corresponding and proportional, and those angles are congruent, but we don't see any angles here. The first thing I want to do is find the scale ratio. So let's take a look at AF, right? So A is the first letter, F is the last letter. And if I were to look at this, I'm looking at V and Z because that's the first and the last letter. So those two, side lengths correspond. So AF to VZ. But note that 12 is just a regular number, and then ZV has a variable. I don't want to work with that because that's not going to help me find my scale ratio. So let's look at CD here. CD is between A and F, the first and the last. So I need to look at the two letters that's between the first and the last for this statement. So that's WY, okay? So I can see that CD in WY, so WY is over here. Look at that, we have two numbers, no variables involved, so I can go ahead and write a scale ratio from CD to YV. So it's 9/6. That's a ratio, but you got to express this as a simplified ratio. So 9/6 simplifies to 3/2. Okay, so then now I'm going to go ahead and do is write 3 over 2 here, because since I have my scale ratio, this is going to allow me to find x and y. So let's take a look at this first figure here. Here's my x, that's FD. So here's FD, the last 2 letters, and it corresponds with ZY. So ZY is here, and it corresponds with FD. So I write x over 10. Then I'm going to cross multiply. So I have 2x equals 30, so x is 15. Okay, so that's the answer for x, and this was me finding x. Let me go ahead and find y. So y is located here. That's ZV. So ZV, the first and the last letter. So it should correspond with A and F. So it should correspond to there. Notice that I'm going from the smaller to the bigger triangle, or trapezoid. I need to stop saying triangle so much. But over here, we worked with the large to the small. So I need to be very, very consistent. So I need to go from 12 to 3y minus 1, not 3y minus 1 over 12. So then I'm gonna write 3 over 2, that's my scale ratio, and I'm gonna equal that to 12 over 3y minus 1. So then I'm gonna write 3 times 3y minus 1 is equal to 12 times 2, which is 24. Basically, I was just cross multiplying here. So then I'm gonna divide both sides by 3, and I should get 8. 3y minus 1 is equal to 8. So then 3y is equal to 9, y is equal to 3. And that's my answer. Okay, so I want to go ahead and take a look at the next page. It says that if 2 polygons are similar, then their perimeters are proportional to the scale ratio between them. And this is really, really important to note, so I'm going to go ahead and highlight that as we get into example 6. Example 6 says if ABCDE is similar to PQRST, find the scale ratio of ABCDE to PQRST and the perimeter of each polygon. So let's go ahead and find the perimeter of this figure here. Notice that we have 2 tick marks here and 2 tick marks here, where one of them is filled in and one of them is not. So if this is 4, then this has to be 4 as well. And if this is 8 because it has 1 tick mark, then this has to be 8 as well because it has 1 tick mark as well. So then everything is filled out for this particular figure here. We have 8 plus 8 plus 4 plus 6 plus 4. If I put all that in the calculator, the perimeter here is 30. Over here, well, we have 3, 3, but nothing here and nothing there, right? So it's really, really hard for me to figure out what the perimeter of this is. So let's call the perimeter of this figure x. Okay, so I have 30 and then I have x. Let's call this the larger figure and let's call this the small figure. So I'm going to go ahead and find the scale ratio. Well, we know that this is my large figure and this is my small figure. So again, large to small. So to find my scale ratio, I'm going to go from large to small. Okay, so here I have CD. CD, here are the letters CD. It should correspond with RS, right? Because it should be the 3rd and the 4th letter. So I should look at the 3rd and the 4th letter for the other statement. So I'm going to go from 4 to 3. So it's CD to RS. So that's 4 to 3. So my scale ratio is 4 to 3. So then let's be consistent, because now I'm going to go ahead and create the ratio between the 2 perimeters here. Again, it's going from large to small, so 30 to x, cross multiply. So I have 4x equals 3 times 30. So that's 90. So x is equal to 22.5. So x is equal to 22.5, or the perimeter is 22.5. Okay? So that's the answer. Let's go ahead and figure out, or let's go ahead and talk about these shortcut theorems, these shortcut similarity theorems that we have here. One of them is angle-angle similarity, the other is side-side-side similarity, and then here's the side-angle-side similarity. So these things are familiar because we talked about how to prove triangles congruent using shortcut theorems, where we talked about side-side-side, side-angle-side, angle-side-angle, and angle-angle-side, right? So the angle-angle similarity theorem states that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So let's go ahead and label this large triangle ABC. So ABC, and then I'm going to label the smaller triangle as DEF. And then we can say that angle A is congruent to angle D, and angle B is congruent to angle E. So if we say that if angle A is congruent to angle D and angle B is congruent to angle E, then we obviously know that angle C is congruent to angle F, right, by the third angle theorem. But this is enough to show that these two triangles are indeed then these two triangles ABC is similar to triangle DEF by what we call the angle-angle similarity. Okay? Now I want to go ahead and take a look at the side-side-side similarity theorems, which states that if the sides of two triangles are in proportion, then the triangles are similar. So let me go ahead and give you an example. Suppose we call the larger triangle GHI. So GHI, and we call the smaller triangle JKL. JKL. Let GH be 6, let HI be 9, and let GI be 12 for this larger triangle. For the smaller triangle, let JK be 4, let KL be 6, and let JL be 8. So then I'm going to prove or show an example of how the side-side similarity works. What we're going to do is see whether or not these sides here are proportional to each other. Okay? They should have the same scale ratio. So if I say that these sides in yellow, so if I say GH corresponds with JK, and then I fill it in, I should get 3/2. And this is in yellow. And then if I were to look at this color to this color, so I will say HI corresponds with KL, so that's 9/6. What goes into 9 and 6 at the same time? 3, so that's 3/2. And then lastly, let's take a look at these two colors here in blue. So it's GI to JL, which if I fill it in, it's 12/8, so that's 3/2 because 4 goes into 12 and 8 at the same time. So notice that they are proportional to each other. So if we have 3/2 here, 3/2 here, and 3/2 here, and we're dealing with the sides here, that's what side is, then we can say that these two figures are indeed similar. So let's go ahead and write this down. If GH over JK is equal to HI over KL, which is equal to GI over JL, then we can say, then triangle GHI is similar to triangle JKL by the side-side-side similarity theorem. Let us move on to the side angle side similarity theorem, which states that if an angle of one triangle is congruent to an angle of another triangle, and the sides including those angles are in proportion, then the triangles are similar. So let's call this triangle MNO PQR, and these angles N and Q are congruent. And then we're going to let MN be 4, NO be 6, PQ be 2, and then QR be 3. So then what I'm going to do is, okay, let's go ahead and find the ratio between these two sides in blue. So I have MN to PQ, which is 4 to 2, so that's 2. And then these sides, NO to QR, that's 6 to 3, so that's 2. And then we cannot forget that angle N is congruent to angle Q. Okay? So, how the side angle side similarity works, just like this. So if these two sides are proportional to these two sides, where the angles are congruent and between those two sides there, those two proportional sides, then we can say that these two triangles are similar. So SAS, SAS. So let's go ahead and make a note. If angle N is congruent to angle Q and MN over PQ is equal to NO over QR, then we can say that triangle MNO is similar to triangle PQR by the side angle side similarity theorem. Okay, so let's go ahead and utilize those similarity theorems that we just talked about. Here are some examples. So we have example 1A. I got the smaller triangle to the bigger triangle. So note that angle L is congruent to angle N. And then if I were to figure out this missing side here, or not this missing side, sorry, this missing angle, well, that should give me 75. Because the sum of the interior angles of a triangle is 180. So that's great. Here, I'm going to use a different color so I don't confuse you. 75 degrees. So we can see that angle K is congruent to angle P. So if we have angle L congruent to angle M and angle K is congruent to angle P, would it be side 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 similarity, angle angle similarity, or side angle side similarity? Well, if two angles of one triangle are congruent to two angles of another triangle, then the triangles are indeed similar by the angle angle similarity. So we can say that triangle LJK is similar to triangle MQP by the angle angle similarity theorem. And that was very, very straightforward. For B, notice that we have these two triangles here. It's a bow tie problem, and see that XR is parallel to WT. So then I know that these two lines are parallel and they are cut by a transversal. So that means that angle R is congruent to angle W, and angle X is congruent to angle T. And we know that these angles here are congruent by vertical angles, but this is enough information to tell me that these two triangles are similar because of the angle-angle similarity theorem. So we can say that, triangle XRS is similar to triangle TWS by the angle-angle similarity. Alright, I'm going to look at example 1C. I have these two triangles where the sides are filled in. And what I like to do is I'm going to compare the smallest number to the smallest number from one triangle to the other, and then the second largest side to the second largest side, and then the largest side to the largest side. So here, let me go ahead and give you a demonstration. So I'm comparing the smaller triangle to the bigger triangle. Know that 5 is the smallest triangle, or sorry, smallest side of this triangle, and then 12.5 is the smallest side of that larger triangle. And then here I have 6, and I'm going to compare that to 15, and then lastly 8 to 20. So then let me go ahead and create my ratios. So I have 5 to 12.5, and then I have 6 to 15, and then 8 to 20. So I'm comparing from the smaller triangle to the larger triangle. And then I'm going to go ahead and get my calculator out, and then I'm going to simplify these ratios and see if they are all proportional. So I have 5 to 12.5, which is 0.4, and then I'm going to press math, enter, so that should give you 2/5. And then I'm going to look at 6 to 15, and press math, enter, so that should give you 2/5. And then 8 divided by 20, notice that it is also 0.4, just like the rest of them. So I really don't need to press math, enter. So that should be 2/5 as well. Okay, so if we look up if the sides of two triangles are in proportion, then the sides are similar. So these ratios here, are proportional. So that means that these two triangles are similar by the side similarity. So triangle PQR is similar to triangle STR by the side similarity theorem. Okay, so let's go ahead and move on to example 1D. So I have a triangle within a triangle. And what I like to do is whenever I see a triangle within a triangle, because if I were to just imagine that this doesn't exist for now, right? So it's just this. And if I were to draw this segment here, you basically have a triangle within a triangle. It's just that this triangle has shrunk. So I'm going to go ahead and draw those two triangles there. I have the small triangle, and then I have the big triangle here. So this is AEF. So AEF. And then here we have ACB. So AE is 8. AF is 10. And we don't know what EF is, so we're going to leave it be. But for the bigger triangle, AC is 8 plus 4, that's 12. And then AB would be 10 plus 5, that's 15. So then we can see, okay, we have the smaller triangle to the bigger triangle. So it's 8 to 12. We can see that AE corresponds with AC. So I can write 8 to 12, which reduces to 2 to 3. Here we have AF to AB, which is 10 to 15. So that reduces to 2/3. So these sides are proportional. But what did I leave off? Well, notice that this triangle within this big triangle, they both share an angle A. This is what we call the reflexive property. So that means that this angle here and this angle here are congruent. So angle A is congruent to angle A. So if these sides are proportional to these sides, where the angles are congruent to those proportional sides, then we can say that triangle EAF is similar to triangle CAB by the side similarity theorem. Okay, hopefully that makes sense. And whenever I see a triangle within a triangle, I like to redraw so I can visualize what the heck is going on. Alright, we're going to go ahead and move on to the next notes, or the last page. Alright, let's go ahead and take a look at the last page of the notes. It says, find the measure BE and AD. Note that we have a triangle within a triangle, and what I like to do is I'm going to redraw those triangles into two. So then I have ABE, and that's the smaller triangle here. And then I have ACD, the larger triangle, so ACD. So AB is 3, and then we have BE, which is X, AE is Y, AC is 5, because look at that, we have that whole thing there, so it's 5. And then AE to ED, which makes AD, right? That's actually Y plus 3, using the segment addition postulate. So then there we go, CD is 3.5. So then I'm going to find my scale ratio from this figure to this figure. So I need to find a number over a number, no variables involved. Notice that we have a number here and a number here. So from the small triangle to the big triangle, my scale ratio would be 3 to 5. So my scale ratio is 3 to 5. So then with that scale ratio, I can go ahead and find BE, which is X. So BE is X. So that means it corresponds with 3.5. So I'm going from the small to the large, just like what I did with the scale ratio. So I need to be very, very consistent because I went from 3 to 5 or small to large. So then I'm going to write X to 3.5. Then I'm going to cross multiply. I get 5x equals 3 times 3.5, which is 10.5. So that's 10.5. So x is 2.1, or that is the measure of BE. To find AD, well, AD is here, and it corresponds with AE. But remember, so let's first of all, I'm going to write my scale ratio. It's 3 to 5. Y plus 3, or AD, corresponds with AE, but where do I put it? Do I put Y plus 3 here or here? Well, just like my scale ratio, I went from small to large, so this has to be small to large. So small to large. So Y has to go up top, and then that Y plus 3 has to be in the bottom. So Y over Y plus 3. Then I'm going to cross multiply. So 5y is equal to 3 times the quantity, y plus 3. So I have 5y equals 3y plus 9. And then I need more room, so I'm going to move this up a bit. So I have 2y equals 9, so y is equal to 4.5. So y is 4.5, and it's asking to find AD. And this is AD. Sorry, I'm going to use a different color. So this is AD. So AD is 4.5 plus 3 equals 7.5. And that is my answer. Okay, so that's the measure of AD. Example 3, Holly is estimating the height of the Cyclone roller coaster in Galveston, Texas. She is 5 feet 3 inches tall and her shadow is 3 feet long. If the length of the shadow of the roller coaster is 34 feet, how tall is the roller coaster? So, here are some things that we need to note. We have the person, who is 5 feet 3 inches tall, and then we have the shadow of the person, which is 3 feet long. And then, if we're talking about the roller coaster, we know that the roller coaster's shadow is 34 feet long, but the question is, how tall is the roller coaster? So here we have our picture. This is how tall the roller coaster is. So this is my roller coaster. This is how tall the roller coaster is. We don't even know what that is. So we'll call that X. That's our unknown. That is what we are trying to solve. Hence, how tall is the roller coaster? Notice that the roller coaster shadow is 34 feet. So it's 34 feet long. So if I were to redraw that figure, so this is, it's X feet long, and the shadow is 34 feet long. Okay, and it's a right triangle, so I'm going to draw a square there to indicate that it's 90 degrees. And then here's the person that I was referring to. So if the person is standing up this tall, standing up straight, and the shadow is perpendicular to the person, just like so, then the shadow is 3 feet long, and the person is 5.25 feet long. Okay, and notice that the 5 feet 3 inches tall got converted into 5.25 feet because we want to convert inches to feet, which they already did for us. So then again, like I said before, if she's standing up tall and the shadow is perpendicular to her, they intersect at a 90-degree angle, and then I can go ahead and close the figure. So then what do I have? I can create a ratio from, so I'm going to go from height to height, and I'm going to equal that to shadow. Okay, so I have 5.25 over x, and I equal that to 3 over 34. So then I'm going to cross multiply, and I have 5.25 times 34, and I equal that to 3x. Then I'm going to simplify, so that's 178.5, equal that to 3x, so x is 59.5 feet. And another way that you can do it, if you want, you can say the height to the shadow, which is equal to the height to the shadow. So you can set it like this, 5.25 over 3, and I equal that to x over 34, and then you'll still get the same answer. See, we have 3 and an x, just like we had before, and then 34 and the 5.25, they remain the same. You should get x is equal to 59.25. So there's more than one way to set up the problem, and you should get the same answer. But nonetheless, the height of the roller coaster is 59.5